Good morning to all participants, and also, yeah. Now we'll begin the next sessions, lectures about introduction to inference from Dr. Tri Astra. But before I will read about a CV, a short CV of Dr. Tri Astra. He's our alumni from Astronomy Institute in Institut Teknologi Bandung finished in 2006, and he got his MSc in University Leiden in 2008, in PhD also in University Leiden in 2013 in astroparticle physics. Now he's in Space Telescope Science Institute in Baltimore, USA, as a postdoctoral fellow. His research area is about data simulation and calibration of the Roman Space Telescope prism, observation of supernovae type 1A, and ground-based astrometric detection of exoplanet in Carnegie Atmospheric Planet Search CAPS program. Okay. I will give time and to Dr. Tri to give his lecture. And before that, do you want Tri? Do you want to the question during the lecture or in the 15 minutes after?
Anytime is okay.
Okay.
Just feel free to interrupt or raise hand. And,
please, if you have it. Okay, thank you. If you all participants, if you have question, please raise hands or write your questions in the chat. Okay,
just
please.
Interrupt me, it's okay.
Yes.
All right, and thank you, and thank you, Pak Iqbal, for the nice introductions. And hello, everybody, and good morning to all. I hope you're having a good time right now, and today we'll continue with something light. It's about inference, just the basic principles. So now pull up a slide here. Share screen. All right. Can you see my slides?
Yes.
Okay.
Yes.
Now, if I do a full screen, do you see the whole screen or just?
Yes, whole screen. Yeah.
Okay. Very good. Yeah. So today we're going to talk about inference, and this will be divided into two parts: the introduction to inference and Bayesian inference in the day after tomorrow. So. And today we're just going to talk about the basics of activities of inference. In fact, the whole course is about inference, if I can say. We just divide the small pieces. So what is inference? There are many definitions, but I like to say that what the inference is extracting knowledge from incomplete information. I say extracting, but you don't get it automatically. You have to pull it out from the whole mess of data. So that's incomplete. So whenever we take data, it will always be incomplete. The incompleteness is due to noise, right? And this is a fact of life. You cannot avoid it. You will always have noise in your data taking. So there are many examples of noise. Here I list just three of the most the more important ones. The whole list can go on. First, the usual stuff. If you're doing experiment, you have measurement uncertainties. because your instruments will never give exact measurements. If you have a ruler, your accuracy will be limited by the tick marks, the distance within the tick marks. If you have more sophisticated instruments, you have microscope to see the tick marks, but still it will be limited by how good the tick marks are marked by the maker of the instrument. So there are limitations in this, and we have to know, we have to characterize it. And then the second one, the most subtle one, is sampling. You see, when we observe something, we can do it at the same time simultaneously with somebody else, but still it's still going to be limited. We cannot. We probably only measure a partial part of the data, but not the other part. Or maybe we can only observe it at one time, but not on the other time. So we have incomplete information with regard to space and time, and spatio-temporal incompleteness. That's the lingo for that. And then the other is the size of the data, or the complexity of the data. The data, we might be dealing with trillions, billions of lines. Like for example, in an astrometric catalog like Gaia, it might be high dimensional, like in the future LSST. There's a lot of measurements being taken. There's a lot of data. And it might be correlated to each other because of the way we take data. So or everything all at once. It's a mess. So it's reducing this complexity is also a problem, a challenge to have to deal with. So we have to and sometimes we have to deal with all of these three things all at once. So if you're doing high level analysis, it can be a problem. Right, and so how do we deal with this? So I'm going to give an example of problems that we've been doing for a long time as astronomers. So collectively, Bosca Observatory people knows this. I did that in the past as a student, and right now I'm also doing that as an astronomer, where we measure the position of stars over several years. Now, is the star single or double? That's a question. So how do we answer that? First, we have to figure out how the data are measured. What are the source of noise, as we discussed? Okay, and then we have to build a measurement model for that. We have to model how the actual measurements is going to be done. So we're going to talk about this in this today. And then we have to think about how the data itself is actually generated. We have to think about the intrinsic nature of the astrophysical nature of our data in this case. We measure the movement of the star. How do they move? What drives them? There must be a generative model, or a forward model that can predict the movement of the star. What are its parameters? If you know that there are several parameters in the stellar movement, for example. They are the motion of the star itself, is called a proper motion. There are the motions due to the star's orbit, it's called a parallax. And then there's the intrinsic movement of the star itself. If it's binary, then there's an orbital model. So this is what we call a generative model, a model that can generate the observation. So now we have to deal with two models. We have to deal with forward model. It generates the observation, and then we have to deal with noise. We have to build a noise model. And then once we have this, then we might have several competing models that might explain the data. The star might be far away, so we cannot observe the parallax. The star might be relatively close, but if there's a companion, it might be too faint, so we might not be able to detect it. So so we cannot. There is no orbital model. Or if we can detect it, then we have to consider models that can models with orbital motion. So then we have this 3 or 4 astrometric model that we have to test. Okay, so then we have to do hypothesis testing. We're not going to do it today. We're going to do it maybe the day after tomorrow. But we'll talk about model selection tomorrow when we're talking about regression. And then finally, is the model good to make predictions? Is it robust? Is it if we observe the star, can it predict new data? Does it accurately predict new data? What if it's wrong? Then we are doing the whole thing wrong. Then we have to restart all over again. Right? So this is a snapshot of what we might do to answer a question. So you must have a proposition, think about a question, think about how all the data is generated, and then do some hypothesis testing, and then make predictions. That's the gist of it. Of course, this is not the only way we're going to do it, but that's one way to do it. So now we're going to talk about measurements, right? We might think that when we're measuring something, we're exactly measuring it, but actually they're not. It's always random. Of course, if your instrument is very good, then the randomness is negligible. But in actuality, there is a randomness. Like for here, so because of noise that we've been discussed about, whenever we measure something, it is not actually the true value. It is always random. So if you see here, before we observe one data, we measure something only once. Now we measure it 5 times. We have 5 different results, right? So 2 of them are close to each other here. So two of them are close to each other here. Can you see my cursor?
Yes,
Right.
yes, we can see it.
Okay.
Yeah.
Okay. Good. All right. Here, so you can see. That's a nice trick. Right. So there's 2 data here and it goes together. So the more we take data, the more we take data, the more it seems less random. Hang on. Yeah. No, there it is. Oh, it's not gone. Okay. No, it's there forever. All right. Right. In the example on the right here, we have 100 data points, and it seems that they are not uniform. You don't find the data all over the place. We find the measurements is quite concentrated on some values, right? So in fact it looks like this form here, the form that we're going to talk about. So we see randomness here. It is derived by probability, our understanding of probability. So it is very important. So now in the next few slides, we're going to talk about probability and how to characterize them. Now, I have to apologize beforehand if you already have seen this before, right? Because this is basically like statistics 101. You might probably have seen this before in classes. I apologize about that. If you already seen this before and you know everything about it, then you can probably do something else, like check your phone, whatever. Right. So here's some basic of probability. What is probability? It's basically a quantification of our state of knowledge about a proposition. Here's an example of a proposition. Okay, that's how you get to it. That is an example of some proposition. This is a spectrum of a star. It will rain tomorrow, or one of my favorite statements: the distance between the stars between 0.8 and 0.5 kiloparsec from the sun. That's a proposition. So we can quantify our degree of belief about this proposition. But however, this is inseparable from our assumption about our belief. This probability is a reflection about our knowledge or current knowledge, whether about the data or about the information at hand. So if you talk with somebody else having the same questions and they have different informations, then I have different probability assessment about the same thing. So we have to be careful about this. What are the basic assumptions? Here are some basic stuff about probability. There's nothing earth-shattering here. Probability have to be between 0 and 1. And if you have a proposition A, its complement is 1 minus the probability of A. So it's not A. And if you have 2 propositions, A and B, and they're independent to each other, and they're mutually exclusive, they're not dependent on each other, then the probability that both proposition to be true is the multiplication of the probability. Right. Now, if we have a set of propositions and they are both mutually exclusive and exhaustive. Exhaustive here means that all of the possibilities are considered and nothing else is possible. And if you sum them all, it has to be equals to 1, right? And then here's the way to write what we call a conditional probability, that the probability of A to be true or occurring depends of B. We said P probability of A given B. So example is rain. A is rain, B is cloudy. So we're talking about what is the probability that it's raining given it's cloudy, right? That's another statement. And then if we have 2 propositions and we want to say, we want to evaluate the probability of both to be true, P and B, we have to multiply. We have to write this. This is how we write joint probability, the probability that A A and B is both true, it's we have to write this: PA given B times probability of B, and the opposite is also the same: B given A times probability of A. I remember that this is not the same. PA given B is not the same as B given A. Remember the statement again. What is the probability of it's raining given it's cloudy? It will not be the same as what is the probability of it's cloudy when it's given it's raining. It's two different propositions. So you can think about it. All right. So some more slides about it. So now if if they are all independent, like B does not depend on A, so you can remove this A thing, and then you just write the B. It's also likewise. So then you just multiply the probability. So this is the probability of A and B to be true, if both are independent. All right. And now we can rearrange this into this thing. This is a fundamental of Bayesian theorem. We'll talk more in this more details about this equation later on. Right, and this is marginalization. We'll talk about this later. So let's skip that. Now here's an example with the missile. You have a missile. It has a probability of 20% chance of destroying its target. What is the probability that the target is destroyed if we fire 2 missiles? I hope you haven't seen my slides because the answer is next. So I'll give you a few seconds. Anybody know the answer? Raise your hand if you know, or write in the chat.
Anyone?
Anyone?
Wants to answer?
Right. Is the answer okay? You have 2 missiles. What is the chance you destroy the target? Is it 0.4? Do you agree it's 0.4? I mean, you fire 2 missiles, and then the chance is 0.2, right? Yeah, Subham, do you know the answer?
0.4.
0.4. Okay. All right. Then, yeah, if you think it's 0.4, it's wrong. I'm sorry. And because let's say we change the probability. It's like 0.6 or 0.8. If it's 0.8, then you have the probability becomes 1.6. So this is incorrect. First, you don't add probabilities when these are two mutually exclusive events. And the second, you cannot destroy the same target twice. So that's why it's larger than 1. So yeah, so how do we think about this? And so we have to calculate all possible events. We have to consider all possible events when we shoot the 2 missiles, right? So here, you shoot missile 1. What is the outcome here? You shoot missile 2. What is the outcome? If they are both miss, then the probability is 0.8 times 0.8. It's 64%, and you're doing it and do it for all of the possible events, right? Then, so what you want is the last 3 rows here. Just sum all of them because in this case you hit the target at least once, right? So how much is this? 36%. So if you fire 2 missiles, your chance is 36% of hitting your target. So you can see if you have n missiles, like 100 missiles, it will take a while to calculate all these tables. You have this table with 100 columns, and you have to consider all of the combination of events. Right? That's quite a lot of work. So in this case, it might be much easier to actually ask the opposite question: what is the probability that all missiles miss its target? As you can see, it's 1 minus p to the power of n, the number of missiles. So the opposite, in which at least 1 missile hits its target, is its complement. So you have the same calculation in a much shorter. In fact, if you want to be a little bit funky about it, then you can calculate what is, if you fire this much missiles, what is the probability that you're going to hit your target 90% of the time. So this line here is the probability of the 90% chance of at least destroying your target. So if you have a really awful, really bad missile, like you only have 10% chance of destroying your target, then you might have to shoot a lot before you're 90% sure that you're going to hit target. If your missile is particularly really good, it's 80%, then you only have to fire 2 missiles, then you have 90% chance already, more than 90% chance already of hitting the target. So that's one way to do it. Right. So now here's another example. You all know about the dice, and it has equal chance of rolling any numbers. It's 1/6. But if you have 2 dice, there are 36 possible outcomes of it. And if you work out all the probabilities, we know that the most likely number to come out is 7. Right, because there are 6 ways to make a 7: 1 and 6, 2 and 5, and so forth. And you can see that 2 and 12 is the least likely number to come out. That's why you have a high returns if you bet on 2 or 12. If you like gambling dice. So if you understand this fact, it will give you an edge on a game of chance. So for example, here Monopoly. So here somebody worked out on how to what is the most important properties in Monopoly. It's the one here. A few steps from jail. What is this? The orange one next to free parking. This is, if you play here like 10,000 rolls of dice, you're most likely to land in this area. So buy this area. Don't think about buying this very expensive part here. It's not really worth it. Right? So that's what we can do with knowing some probability. Right? And if you fancy to be a Monopoly World Champion, you can read the link. Right. So we have seen that the probabilities can be distributed. Some values are more likely to come than the other, depending on the type of distribution. So this distribution that we're looking at is actually for discrete events. So you cannot have something in between, but you can also have continuous variables, like the measurements that we did, and actually this distribution of values, it can be characterized by what we call a probability density function. It's called PDF. So now we're going to talk about PDF. So PDF is just it's actually give a density. It's just as the name says, it's not probability. Right? It gives you infinitesimal probability in a value between x and a very small value. If you want to get a probability, you have to integrate it between a range. Let's say here between x1 and x2. So if you integrate the function between these values, then you get a probability. We'll talk about the meaning of this later. So and a PDF, it has to be normalized. If you integrate it from its all relevant values, it has to be 1. And if you want to normalize it, this is how you do it. So here's some notation. Here's some notations that people like to use. If you have p star, that's usually an indication that the probability is not normalized. And this is how you normalize it, just divided by the this integral here. Right. Then probabilities is a function. It has a parameters that you can also characterize. You can characterize it with some numbers. One is expectation value. So integrate it with x, and can also calculate variance. That's the distance between x to expectation value squared. And if you work it out by hand, you'll get this. Right. So there's a lot of PDF, probability density function. We're not going to talk about everything. I can recommend some books. A lot of statistic books will cover different kind of PDF, but we're going to talk about the 2 most important ones here: Gaussian and Poisson. So you know about Gaussian, you learn it at school. That's it's everywhere. So that's why it's called normal distribution. So this is the form, and it's fully characterized by just 2 numbers: the mean, where the function is centered, and the width of the function is sigma here. So we just need these 2 numbers. Sigma is to be larger than 0. That's several kinds. That's several PDF, Gaussian PDF with different widths. And but they all center to 5. Another is Poisson distribution. Poisson is it's a distribution that gives you discrete numbers. So if you know the rate of expected event, then you can calculate what is the probability you'll get R. So here, for example, if you expecting a very rare event, like you only expect one event, it's more likely you'll get either 0 or 1. So obviously, it's not appropriate to get to use Gaussian. But notice here, the more you expect more event, the more it's get closer to the Gaussian. So in fact, if you approximate it to a large event, yeah, you can approximate it to a normal distribution if you expect a large count of event here. So right, so you can integrate a PDF from infinity to a certain value. This is called CDF, cumulative distribution function. It tells you what is the probability you'll get X, Q or less. Here's some CDF for Gaussian for the same Gaussian function. It's probably appropriate to talk about a mean, about a median. So a median is another estimator that we can use aside from the expectation value or the mean we have discussed. So a mean has to satisfy this relation. If you integrate it from -infinity to m, it has to be 50%. Or the opposite, from m to infinity, it has also have to be 50%. So that means what is the value in which you'll get 50% of the sample is less than this value, and 50% more than this value. So here's the illustration. So you have 3 estimators: the mode, which is the value at which the PDF peak. So here, that's the median. 50% of the sample we have, or the values that we might possibly get, lies here, and 50% that more than this median over there. And the mean, which is the expectation value we have discussed before. They don't have to be necessarily the same. In a Gaussian, all three they have the same value, but here, if you have a skew here, you can have 3 different estimators here. What do you want to use? What do you want to report? That all depends on what kind of information do you want? What kind of information do you want to show? There's no right answer. We'll discuss it later. Right, and then another terms here, it's what we call credible interval. This is just basically the probability of getting values between this range, x1 and x2. Right, so you can say that if you write this down, you can say that this is the probability of finding x lying between x1 and x2. Right, so usually use this for what we call confidence interval, credible interval. If you set up p is 90%, and then we calculate this range x1 and x2, then you can say, oh, 90%. I'm 90% sure that x will be between x1 and x2. But be careful that the opposite is true. There's a 10% chance that x is actually outside the range. Now, if the probability is Gaussian, people like to also create credible interval in terms of the standard deviation. So if you say 1 sigma credible interval, like between here and here, you can say that the value is 68% chance to lie between that range. If you want to be more wide, like here, 3 sigma, then you say that yeah, I have 99.73% of finding x between this range. So of course, you can also say that wider, like 5 sigma, and later we shall see. We can also transform our confidence in terms of this Gaussian standard deviation. Right. Yeah, and here's another thing. If you have 2 variables, x and y, you can calculate the covariance, which is how they dependent on each other. Right, so here I make a simulation of correlation coefficients, this value. So the covariance is usually normalized to its standard deviation. So we usually think about correlation coefficients. So correlation coefficients can only lie between -1 and +1. And here's what your data look like if you have 2 dimensions, x and y. So if you have positive correlations, y will depend on data positively. If you have -1, it will depend on X negatively. So if you have 0 or close to 0, that means they're independent and uncorrelated of each other. Now, if we have 2 or more variables, we can form what we call a covariance matrix. Here, this is going to be important later on. So the diagonal here describe the sigma, the standard deviations, while the off-diagonal components that describe the covariance between, for here, for example, between variable 0 and variable 1, and so forth. Now we can see here, this guy here is the same as the off diagonal is symmetric. So this guy here. So this guy here, as you can see, it's the same as this guy. So they're symmetric. Okay. Right. Right. So now we have described a covariance matrix. We can talk about multivariate probability distribution. This is a PDF in which where you have 2 or more values. So this is how we do a high dimensional analysis, where we have to think about multivariate PDF. We'll encounter this a lot later in the whole of this course. I'm just going to describe multivariate Gaussian. It looks like this, right? It's yeah, that's scary. But one thing you have to say, one thing that you have to think is that this guy here, this is a scalar. This is not a matrix. And of course, this is a vector. This is a vector. This is a 2 by 2. This is k by k covariance matrix, and we have to do all of these calculations. And then this is how we write the Gaussian PDF in k dimensions. Now there are a lot of other forms of multivariate PDF that you can have a look. But let's consider 2 dimensions. In 2 dimensions, the vector of variables is xy, for example, and its mean is this, and the covariance matrix is this. And if you work out all of that, you'll get this, and here, and this z. Z is this one. So you can work it out yourself. It's quite simple, just to give you some idea. Here's an example of a bivariate Gaussian. It's centered on 0, and it has a correlation of half. So that's what it looks like in 3D. That's the probability of finding infinitesimal probability of finding x and y here, for example. It's this one. It's less likely to find it than this area here. So that's bivariate Gaussian. Right, and then another thing is if we have multivariate probability, usually we don't really care about all of the other variables. We only want to see what is the probability of x. But we have a joint probability here. So for example, in 2 dimensions. So what we have to do is we have to integrate them. We have to integrate the y's out. So if you want to get the probability of x only, we have to integrate y over all of possible values of y. Right? So we have to consider this is what we call marginalization. We call this x marginalizing over y, and this px is called the marginal PDF of x over y. So think about this as we look to here, to this line here, but we're summing up everything we see. So that's the process of marginalization. So that's everything about probability, PDF, and all of the activities that we can do about it. So now we have how do we use these tools to infer values from data? We can assume that, like for example, we measure data, and we can assume they are drawn from what we call a underlying parent distribution, and we want to know what's the distribution looks like. So in order to do that, we use an estimator. Now, an estimator contains a statement about what we think about what the probability looks like, and how it interacts with the data. So we have to think about it carefully. So there are sometimes we distinguish between 2 different estimators. The point estimator, it gives you median mode, or interval, gives you range. It's also possible that if you have samples, then this is an estimator of the parent distribution itself. I will talk about this later in MCMC. So here's our data again. The same thing that we showed earlier. So we measure a quantity 100 times, and we see that they're not uniform, right? They concentrate to certain values. So we think this might be, we can characterize this as a Gaussian function. We can say that the data is generated from a Gaussian distribution, and we want to know what are the properties of the Gaussian, what are its mean and its standard deviation. So we write down a measurement model here. So this is the probability of observing X, a single data point, given the parameter of the Gaussian. It's just simple Gaussian. So now, if we have a set of n data points, what is the probability of observing all data points? Is the product of this. So we want them all to be true within the uncertainties, within the standard deviation. So we multiply them all, and we take the natural logarithm of this, because this is much easier to work with, and they're not very concentrated to a peak. It's much easier to handle. So if you take the natural logarithm, you'll get this. The exponent's gone. Now, what is the best value of mu here, of the mean, right? Well, it must be the value that give the maximum probability, maximum combined probability, right? So how do we find it? It's just the usual. We differentiate it, take a partial differentiation with respect to the mean, and then we set it to 0. So that's our best estimate. It's actually just the sample average. So the mean is just it's just the average sample of all the data we have. That's our that's what we call our estimate of the mean. Now, if you do the same for the standard deviation, we also get the estimate of the standard deviation of the parent distribution. So if we compare it to the two distribution marked in green here, it's very much close to the two distribution. So it's not bad, because our assumption is true. We assume the data is generated from a Gaussian distribution, and it turns out the data is it's like so. So this is the case where we have correct assumptions. So how do we estimate the uncertainty of the mean? So we estimate a mean. It must have an uncertainty, right? So let's have a look. Let's calculate the log likelihood here. As a function of mu, as a function of the mean. So let's try to change the value of the mean. I mean, it's just one dimension. So if we test it and we find that the maximum is here, this is the one that we already have found. And you see, there's a width here. So there is a chance that the actual mean is actually somewhere here. So there's a width here, right? And this is what we want to measure. This is a measure of how uncertain our estimate here, right? So then we calculate the slope, the curve. And so we change this a bit, and we do Taylor expansion. So we expand this function into a Taylor series, and this is what it looks like. And we already defined this to be 0, right? Because this is the maximum likelihood. Now, if we're rearranging all of the order, we'll get something like this. Now, I encourage you to work this out yourself to check whether this is true, and look at that. What does this looks like? It looks like Gaussian, right? So I can rewrite it like this. Get rid of this. It looks like a Gaussian. So this is the likelihood in terms of this is the estimate of the mean. Sorry, I don't write it correctly. No. Yeah, sorry. No, this is supposed to be the probability of the mean. Right. So anyway, if we look at this, we can. This is the variance of our estimate. You know. This is the variance of the mean. So it's actually the second derivative, but then you have to make it negative and then inverse square root. So, and if you calculate it, it's going to be like this. You know, that's a so it's just the sample variance that we already calculate and divided by the square root of the number of data. So that's why whenever you want to estimate the quantity, you take the mean, calculate standard deviation, and divide it by the square root of the number of data you have. That's the accuracy of our estimation here. So it stems from maximum likelihood estimation. So you can see why we use it all the time, because we assume it's Gaussian. So so remember about this fact. This might not be right if the data is actually not Gaussian. So so that's how you do single parameters. Now, if you say now, here's another case. Suppose we measure quantities, but we know the standard deviation of our measurements, and then we measure another data, and then we take another data, and then we know the uncertainties. Let's say we have measurements from various laboratories all over the world, and they all have different instruments, but they're measuring the same quantities. You know, and they all have different uncertainties. So how do we combine it? It's just the same. You know. Just write down the PDF once again. Just assume it's. But now it's not uniform. This is what you call a heteroscedastic data. So data with non-uniform uncertainties. You know, so there. So we do the same thing all over again. Write down the probability of writing. Write down the probability of obtaining all of the data set. And if you take the natural logarithm of the likelihood, you'll get this. And if you do the whole thing again, this is our estimate. So it's no longer an arithmetic mean. It's a weighted arithmetic mean. The weight is the variance of individual measurements. So that's why it's different. What's the uncertainties? That's the sum of the weight minus that's inverse square root. Right. So that's some basic introduction of inference. You know, where we have quite a lot of time to do a lot of discussion. So here's some of additional thoughts that I have input. So as we can see, whenever I talk about probability, it's not only about frequency. We might usually think probabilities as frequency, like how often an event happens. If the probability is 20, if you have 100 event, then 20 times you'll observe it. This is you can say that, but sometimes it's not always the case. So that depends on the context. And then another thing is always things about the noise model of our data. How does the data generated? What are the source of noise? Is it Poissonian or is Gaussian? What is the most appropriate one? So we're dealing with Gaussian noise here, but our experiment might not be Gaussian at all. It might be Poisson. And the second thing, and the final thing is that this is all point estimation. So we try to report a single values, whether it's the mean or the median or the mode. But it does not actually report the whole PDF. If your PDF is Gaussian, then then you're lucky. Just the mean and the variance is enough. But what if the PDF is a funky looking PDF? I'll show you a funky looking PDF later. So So it might not be appropriate to just estimate 3 points about to summarize the whole distribution. We might to actually see what the whole PDF looks like. So we're going to think about it later, how it will help improve our inference. So that's everything for today. If you have questions, feel free to ask. We have about 45 minutes.
Yeah. Okay. Please raise your hands if you have questions. Please. Okay. From Visa, please.
Yeah, hello. I'm audible.
Hi.
Yes. Okay, please.
Thank you for the great lecture, sir. Actually, so I had this doubt that you mentioned, we should find the minimum, like we find the best estimate using a differential, right?
Yeah. No. It's not a minimum. It's a maximum probability.
Yeah. Sorry, maximum.
Yeah.
So how can we make sure that it's not a local maximum and it's a global maximum?
Okay. Yeah, that's that's a whole important question also again. If we look at the form of the PDF, then look at the wide range of values, and you don't see another peak, then you can be sure that this is a global maximum. I mean, if you look at the form of the PDF of a Gaussian, if we have a lot of data, this is actually a multi-dimensional Gaussian. And Gaussian, if you take the differential, it only have one peak, right? So mathematically, for some kind of distribution, we can prove that if you take the minimum, it's a global minimum. But in certain case of kind of PDF, like if you're doing orbital parameter determination, so you want to determine the orbital parameters of a double star, or you want to find the parameters from light curve, right? Sometimes what we get is not a global maximum. You're actually trapped in a local maximum or local minimum. So what we have to do is we have to use for this, because this is multidimensional, use MCMC, Markov chain Monte Carlo, to sample the posterior of a whole wide range. There are several techniques to do that, and okay, since you're asking, I'll probably have to put that in my materials. I will talk about this Tuesday, Wednesday, or how. So the whole idea is that we do a parallel random walk, right? So we set up different location, and then they explore the local posterior, and then they'll compare the means, and then and then they'll compare the value of the PDF with each other, and then they're going to move to the location where there is a maximum probability. So that's the gist of it. But there are some details. So yeah, so in principle, depending on the kind of probability you have, you might not know whether this is. You might be able to prove this is global maximum, but in some cases, you might not be able to do that. This is actually a difficult problem. So, but there are some ways. There are some ways to find out, but doesn't really guarantee it. You'll get the right one.
Thanks.
I hope that answers your questions.
Thanks.
Okay, thank you, Visa.
Yeah. So Arifin, please.
Arifin?
Oh yeah, hello. I'm sorry. I think my internet is just a bit wavy.
Right.
Okay.
Right.
Thank you. Thank you for the explanation. I'm really curious. So I don't know whether this is also the field of your work about making instruments, because as we know, like you said before, we have to assume not just the source, but also the probability of how the instrument will react to a certain signal. So how do you manage that? That there's this layer, or probably there's complexities in the real designing of an instrument.
Yeah, and the very simple. Yeah, that's a really good answer. That's really good questions. And instrument characterization is also a whole different fields. It's not only us astronomers, but we also talk with engineers about what do we want with. You want to build an instrument, let's say infrared instrument. We want this to reach a certain signal to noise level. How do we do this? And usually engineers with more knowledge about materials, they will think about something like CCDs, for example. CCDs has a certain noise. You can characterize a CCD from certain parameters, like what is the readout noise. So when you transfer the electronic to the readout, there's noise. You can characterize that. You can test using some techniques like calibration stuff. So you put a light. You know the illumination of your light. What is the uncertainties, and then we count how many photons do we record. What is the variety? So there's a lot of techniques to do that. Like, are you from ITB?
Yeah, I'm a master's student.
Okay, yeah. Pak Hakim should be able to answer the questions about this. Yeah, I did a lot of work with Pak Hakim on how to characterize a PMT, a photomultiplier too. Right, so we calculate the response rate of the quantum efficiency of it. That was a long time ago. So in principle, the answer is calibration. Lots of calibrations to understand what is the source of noise from an instrument. So we have to understand about materials. How does it records data, and what is the possible source of noise? Like, for example, in a CCD, it works with a photoelectric effect. So we have to understand all of this way it's going to produce electrons, and how it's going to be recorded. And finally, the bottom. What is the bottom line? Can we get some numbers of it? So that's why you get you have, if you look at the CCDs, you have these parameters: readout noise, what is dark noise, and all of the things. These are measured to careful. These are estimated to a calibration process. Like for example, we have, there is a screen, and we shoot light to it. So you have even illumination on the screen, and then you let the camera record. If you've been to Bosco Observatory, you'll see it in action. And also you compare it with the sky measurement. So you measure the sky brightness during sunset, because it's even illumination. It works like a flat field actually. So you compare the results. So there is a lot of methods on how to do it. But yeah, so the key is instrument characterizations, and yeah, there's a class to do that at ITB, and I suffer to it. But I hope that answers your question.
Thank you very much.
Okay, thank you, Arifin. Any more questions? Please raise hand. Okay, CG, please.
Hi, Dr. Chi.
Oh, hi.
My question is, how do you know that your assumed distribution is appropriately used? How do you know it's correct?
Yeah, that's another important question. So we do a hypothesis testing. So there are several tests for that, and it's like KS test, Kolmogorov-Smirnov test. So you have two distribution, and then we do this test of how close they are to each other. So and then we find the optimum value. So you can do that by so you have this data, and then we have another data. Maybe it's randomly generated from a distribution that we know the parameter, and then we do the test. Or that's one way. Or another is just like that. So it's just like the whole exercise that we did, but this one with a different distribution. So you test another one. then we see which one best describe the data. There are several statistical tests for that. So, that's the way to do it.
Thank you.
Okay, thank you, Cici. Any more questions? Yeah, Arifin. Okay.
Okay.
Jan, please. After Arifin, and then Farah. Arifin first.
Okay. I hope this is not out of the topic, but I'm curious, what is your current research now in the Space Telescope Institute?
Wow. Okay. All right. Yeah. So I'm doing a lot of data simulations with Roman Space Telescope. So Roman is a new NASA flagship mission. It's made of reuse spy satellite donated from the NRO. It's like the CIA, but intelligence agency, but a different kind of thing. So they have a use spy satellite. They give it to NASA, and then NASA will use it for infrared survey mission. So it's called the Nancy Grace Roman Space Telescope. It's going to do a lot of stuff, but what I'm involved with is it's going to do supernova survey, so using a very wide field camera. So we want to observe supernova ever more carefully. So the specific things that I'm doing is I generate a fake data, fake galaxies, as observed by Roman, and then I try to reconstruct the 3D data cube of the spectra. So what is the 3D? So the data cube, so you have an image, a monochromatic. You have an image, and then at each point you have the wavelength. So it's like an integral field unit. But the problem is this is a slitless spectroscopy, so you have to figure out a way to deconvolve. It's a difficult problem. Yeah, and I also try to detect exoplanet using astrometry from my previous work. We can talk about this offline.
Thank you very much.
If you want to know the details.
Yeah, maybe we can give you a Slack channel, 3.
Yeah,
so
yeah.
all
I'm
participants can discuss anything with you.
Yeah,
all
I'm
about
already,
the lectures also.
Yeah, I'm already in Slack, so you can find me there if you have more questions. Yeah, don't be shy. If you're too shy to ask it here, you can also contact me in Slack.
Okay, thank you, Arifin. Next, Farah, please.
Hello, Mr.
Hello. Yeah, hello.
Yeah.
Yeah, I can hear you. Just speak up a little bit.
Yeah. Yeah. My question is it possible that if a data has like two peaks, like two peaks, how to do the inference for it?
Yes, that's very good questions, and yes, you can have what we call a bimodal distribution. That means we have two peaks, or in fact, it can also be multimodal. We have a lot of peaks, so that's quite a mess to work with. I can. Again, this depends on what you want. If you want to find the most, and this is also related to the questions by Fisak. How do we find the global maximum of a PDF, right? So if you have a multimodal PDF where you have a lot of peaks, so not only two, if you can identify all of the peaks and the most important ones, then the question is, what do you want to know? There are two ways to. If you want the most likely peak, then you pick the mode with the highest probability. But regardless of the natural intrinsic astrophysical nature, you might get a mode with the most likely peak with the maximum probability, but it might not be physical in nature. It's probably because of noisy data. So this might not be the real peak. The real peak might actually be the one that's not really probable. But if you have an additional assumption about it, then by all means use it. Then you can probably incorporate it. You include it in your inference, and who knows, your results may change. So we are going to talk about this phenomenon later on in Bayesian inference. We'll see PDF with lots of peaks.
Sir, I would like to ask, is it the same if the data is like a continuous data, like for variable stars, the period will like continue in like a phase? Is it the same for that type of data too?
What do you mean? Can you?
I mean, like variable stars. Some of them like periods of time. So the data are continuously like in a loop. Yeah.
Yeah. Yeah. So that's that's a periodic data. So so the challenge is to find the right period. So how to find the periods in which if you fold the data to its period, then it will come back the same, right? So that's a problem. There's also a different problem altogether. What we can do is we construct a periodogram. So we pick a period and then we calculate, and then we keep it fixed. And then for this period, calculate the parameter of the model, and then see what's its residual. So what's the find some what's the likelihood values, and then pick another period. So you have this grid of period. Yeah, maybe in log space, and then you look at the and then we look at the functions. What is the most likely period? It's usually the one with the least residuals. But other people have different criteria.
So for periodical data, we can marginalize it, like just a certain range.
Yes. Yes. Now you can also write down the probability of joint probability of all of the parameters, and then you sample and then we sample the posterior, and then we marginalize it. I just want to know what is the distribution of the probability, considering all of the other values. So yeah, if you're doing orbital analysis or light curve analysis, we're going to deal with it most of the time. So if you don't care about all of the other values, you just want to know what is the period, then we collapse all of the PDF into a single dimension. That's the period. All of the other are marginalized. So you can do that.
Okay, thank you, Mr.
All right.
Okay, thank you, Farah. Next, Ehsan Mauli, please.
We can hear you. So you're still muted. Okay.
Yeah. Oh, maybe there's a problem with your mic, Ehsan. We cannot hear you.
Okay. Write down the questions. I'll try to answer.
Yeah.
Oh, yeah,
am I audible now?
Yeah, I can hear you. Oh, good.
Yeah. Okay. Good.
Thanks. So my question is actually related to what CJ asked. Suppose we have data and we don't know what the underlying distribution is. So, for example, we have some data and say we estimate that it's either a normal or a log normal distribution, and we do a maximum likelihood estimation of the mean. So is there any way to compare the two means that we have gotten based on the two different distributions and directly compare it and know which one fits the data better, or is there some other hypothesis testing that we have to do?
Yeah, you have to do hypothesis testing, and there are a lot of ways to do it. Yeah, I mentioned the Kolmogorov-Smirnov test. That's one way to do it. That's people usually like that. And or no, I haven't done this in a long time, so I have to look it up again. So yeah, KS test is the the more popular ones. If you have several, you can compare one, can do pairwise comparison, and then see which one give the best values.
Right.
Probably the way to do it.
So we can't directly compare the values of the likelihood between the two models and say which one fits it better. We have to do hypothesis testing.
Yeah, so you have to be careful about how you write the hypothesis formulations. What are the assumptions, so that you can be confident that this is the right one. We'll discuss this maybe the day after tomorrow.
Thank you, Isan Moli. Any questions again? Please. Yeah, inference is a basic, statistic and statistics. So we have to understand the basics. Any questions again from participants? Okay. Yeah, from Fikri, please.
Okay, can you hear me?
Yes,
Yes,
please.
Sima.
Yes.
Okay, thank you for your explanation, Mr. Um, my question is rather trivial or just inappropriate.
Don't worry about it.
Is it true that when we measure something without knowing the measurement uncertainty, we can measure the sigma and the mean, given the assumptions of Gaussian distribution and same uncertainty? What makes it different than if we know the uncertainties before?
Yeah, that's another important question. If you make the wrong assumptions, you'll get systematic errors, right? So your values might be different. Might be different than the true values. Now the problem is we don't know the true values most of the time. So sometimes we're not aware of it. That's why people can come to the wrong conclusions. I'll show tomorrow in the regressions that if you have a wrong assumption, you'll have wrong results. And that can happen. So if you don't know the uncertainties, well, there are ways to estimate that from the data itself. So you write them. So we write them in the model as well. So you have a noise model, but we don't know the uncertainties. So you have to estimate it from the data itself. There are ways to do it. Tomorrow we'll discuss about it, and also in MCMC on how to estimate the noise. So this is very useful. And as you can see from the slides before, even if you assume a Gaussian distribution with uniform uncertainties, you don't actually need the uncertainties, right? If you want to estimate the mean, turns out you don't really know the uncertainties of the measurements, but rather we can estimate it from the data itself. Just calculate the variance. Okay, this is your measurement uncertainties, and this informs our estimate of the uncertainty of the mean. So that's one way to do it. So if you don't know the uncertainties, that's okay. You can write this down on the likelihood, and then estimate it from the data. So there are ways to do it.
Okay, thank you, Fikri. Next, Rafi, please.
Yes, am I audible?
Yes.
Okay. So you told that Kolmogorov and Smirnov test is mostly used in the goodness of fit test. So what is the difference between chi-square test and Kolmogorov's
It's okay. That's I don't recall a lot of it, but if I remember, a chi-square test assume that the underlying distribution is Gaussian. So that's so if you're doing chi-square test and comparing between certain parameters, we assume both of these are Gaussian. Now in a KS test, it's a non-parametric it's a non-parametric test. That's why people like it. It doesn't assume anything. It's just calculate the difference. I don't actually remember how it works. I have to read it again. But yeah, but the most important feature of the KS test is it doesn't assume any underlying distribution. So that's the major difference with the chi-square test.
So are there
I hope that
any other any other goodness fit tests beside KS test which are non-parametric, like?
Yes, there are several. There's a lot, and all of them has different assumptions about the underlying PDF. So it's always like that. Like for example, Bayesian information criterions and all of that. So, yeah, I'm not. I'm not familiar with all of them. So I usually just use things that is quite reliable. Yeah, like BIC or cross validations and all kind of things. So, yeah, I'll try to answer your question further later on. I have to read up again.
Thank you.
Okay, thank you, Rafi. Any more questions? Esan Moli again. Yeah, okay, please.
Hi. So
Hi.
you mentioned in the slides that to find the standard deviation, we divide it by n-1 instead of n,
Yeah.
and it's a rather long reasoning behind it.
Yeah.
So is there any way you can explain it briefly, because I don't understand it?
Yeah. So we because the way we derive it, we use the true mean from the. If you look at the slides, yeah, I still have it here. Hang on. Yeah, the main reason is that where is it? Here. Yeah, because if we start from here, and then if we start from here, and then we do partial differentiation with respect to the standard deviation, to the variance, and we work out, we get 1 over n here. Now here it's because actually this is the mean, the true mean. So that's why we divide by 1 over n. But the problem is we don't know the true mean, right? So that's why if we derive this, if we derive the expectation value of the variance from the sample, we'll come at a different results, which is dividing by n-1. So that's the reasoning, because from here we start from we use the true mean, which we don't know. So if we use the arithmetic mean from the data, then you divide by n-1. So if we use the arithmetic mean here, but we divide by n, this will be underestimate. So underestimate the uncertainties, and that's why it's called bias estimator. So that's one of the line of reasoning where you have to divide. If we use the estimated mean here, the true mean, then this is what we use. So I hope that that answers your question. So we start from. So another way to estimate the variance is to calculate is to start from the expectation function, and we'll get a different results.
Okay, thank you.
I hope that helps.
Yeah. Okay, thank you, Esan Moli.